Okay, honors chemistry people, we are going to do a lab today, and I need you to open up your workbooks to page, let's see, what page are we on? We are on page 304. So on page 304, you should have this in front of you. It says Honors Chemistry, Banks Hummer Lab Molecular Models. Now, normally in a non-COVID year, we would build these models using what we call Molly-Mod sets, which I like to call chemistry Legos. They're basically different chemistry balls and sticks that we will put together to build molecules so that we can see the three-dimensional shapes and the bond angles and how things work. This time around, we are not going to use Molly-Mod because COVID, and a lot of you guys are home, and I don't want you guys touching things and handing them off to each other. So instead, we are going to use pHET. So you're also going to want to have pHET out in this. So if we look at pHET and go to the pHET website, we want to get to the bottom of that pHET website where we have physics, chemistry, and math and earth science. We're going to click on the chemistry, and these are all the chemistry pHETs that they have. We are interested in the pHET that is called molecule shapes. It's right here. It's got this black screen with this molecule here, molecule shapes. So we're going to click on the molecule shapes, and we are going to download that. You probably won't download that onto your Chromebook. And the one that we don't want the real molecules, we want the model. So we're going to create these models here. Okay, so let's go back to the lab paperwork. So if I go back to the lab paperwork, the first thing that we need to do is we need to fill out this grid here. So here we have pairs around the center atom, which I like to think of more as electron areas around the center atom. How many areas of electrons do we have? We have bonding pairs. How many of those areas are bonding pairs? How many of them are non-bonding pairs or lone pairs? So this could also be thought of as a lone pairs. Then we're going to have the molecular shape, and we're going to have the bond angle. So let's do a couple of these so that you know how to fill in this table. So you're going to use this paperwork to fill things in, and then you're going to take the questions that are on this paperwork, and you're going to use what you filled in to answer the questions on your Canvas assignment for this lab. So here we've got 4 pairs around that center atom, or 4 areas, and they're all bonding. So let's go to the pHET and let's build that. So right now I have 2 bonding areas. I want to put in another one. So I'm going to add in another one, and I'm going to add in another one. Okay. Now the thing that we really need to see for this, we want to see the molecular geometry. So you're going to want to click that. And we also want to see the electron geometry. Okay. We also want to see the bond angles. So you're going to need all 3 of those clicked: the molecular geometry, the electron geometry, and the bond angles. All of those need to be clicked. So if we look at this, our molecular geometry here is tetrahedral, and our electron geometry is tetrahedral. We are really interested in this molecule geometry. Notice I can take this molecule and I can flip it around so that I can see the shape as it is in all 3 dimensions. And if we look at this, we've got our molecular geometry of tetrahedral, and we have got a bond angle of 109.5. So that is what we're going to want to put on our sheet here. So our shape here, we have tetrahedral, and we have a bond angle of 109.5. Okay? So if we look at this next one, we have 4 areas, but we only have 3 bonding areas. So we have 1 lone pair. So let's go back to the pHET, and we want to get rid of one of those bonding areas, and we want to add a lone pair to it. Okay? So notice we have 3 bonds here. 1, 2, 3, and we've got a lone pair. We still want to look at our geometry. So notice our electron geometry is still tetrahedral, but our molecule or our molecular geometry here is trigonal pyramidal. Our bond angles are still 109.5. In reality, this lone pair right here would take a little bit of extra space. We would expect it to be about 107, but it really depends on the electronegativity between these molecules, how much space those electrons take up. So when we fill this in, we will put trigonal, pyramidal for our shape, and we will still have a bond angle of 109.5, sorry. Okay, so I want you to follow this table and create a table for you to get the shapes and the bond angles using this pHET. Okay, once this table is filled in, then I want you to go to, we're going to ignore these balls, red balls for oxygen, white balls for hydrogen and stuff, because we are not going to use the Molly-Mod sets. We are going to use this pHET. So the next thing what we're going to do is we are going to look at these individual molecules, and we are going to figure out the total valence electrons, the Lewis structure. We're going to do both types of shapes. We're going to do the electron shape, and we're going to do the molecular shape, both of them. Okay, so I want both shapes. I want the bond angle, and I want the polarity. Okay, so let's do carbon tetrafluoride together really quick. So the first thing we want to do is we want to look at carbon and fluorine and see how many valence electrons they have. So if I look at carbon, I've got 4 valence electrons. And if I look at fluorine, I've got 7 valence electrons. Okay, so let's go back. So carbon is going to give me 4 valence electrons. Fluorine is going to give me 7. Now notice I have 4 fluorines, so I need to multiply that by 4. So 7 times 4 will give me 28, plus 4 more gives me 32 valence electrons. Okay? The next thing I need to decide is what is going to be my center atom. Now remember, we always use the less or the least electronegative atom except for hydrogen. So if we look at carbon versus fluorine, remember, we've got carbon, we've got fluorine right here. Electronegativity is greatest in this upper right-hand corner. So carbon is less electronegative than fluorine. So we are going to put carbon in the center here. Okay, so I'm going to put carbon in the center. Oh my, that took my blue dots from the previous page. Okay, I'm going to put carbon in the center here. I'm going to put individual single bonds to each of the fluorines. And now I have to satisfy everyone's octet. Carbon is already satisfied because I've got 2, 4, 6, 8 electrons with that carbon. Okay, so carbon already has 8 electrons. I've used 8 electrons, so I still have 24 to place. 24 divided by the 4 fluorines is 6 electrons each. And each of the fluorines already have the 2 electrons from the bond, so they do need 6 electrons, or 3 lone pairs, to satisfy their octets. Okay, so when I look at this, fluorine's octets are satisfied, carbon's octets are satisfied. I've used 2, 4, 6, 8 electrons on each of those fluorines. 8 times 4 is 32. Carbon satisfied, so I have used my 32 valence electrons. Okay, so now it's time to look at this with the pHET. Okay, I have used 4 single bonds. There is no area around that center atom that is a lone pair or a double bond. So I've used 4 single bonds. So I'm going to go back to this pHET. I'm going to take off that double bond, and I want to put on another single bond. So I have 4 single bonds. So if I look at this molecule, my molecular geometry is tetrahedral, and my electron geometry is also tetrahedral. Okay? So when I fill out my paperwork, my electron geometry is tetrahedral. My molecular is also tetrahedral. So that is my geometries. Now, if I look back at the pHET, my bond angle is 109.5. Okay? So my bond angle here is 109.5 degrees. Okay, now the next thing to do is figure out polarity. Now, polarity, we have to look at electronegativity. So let's look at electronegativity really quick. So if I look at electronegativity, fluorine has an electronegativity of 3.98, and carbon has an electronegativity of 2.55. So let's figure that out. So fluorine has an electronegativity of 3.98. Carbon has an electronegativity of 2.55. Now I want to find the difference of this. So 8 minus 5 is 3, 9 minus 5 is 4, and 3 minus 2 is 1, 1.43. Now, anything that is really bigger than like 0.2 or 0.3 is going to be electronegative. So we do have, let's get another color here. We do have dipoles going towards the fluorine. The fluorine is much more electronegative than the carbon. Now let's look at this three-dimensional shape that we have of the carbon tetrachloride on this pHET. Now if I put these dipoles on each of these bonds are exactly the same dipole. They're the same strength. They're all equal distant from each other. The bond angles are all equal distant. So if I have for everything equal distant and equal strength, when I add them up, what does that mean for those dipoles? Do I still have a dipole when I add them all up together? Hopefully you said no, because if I have all equal distant dipoles and all equal strength dipoles, they're all going to cancel out when I put them on the whole entire molecule. So when I put them over that whole entire molecule, even though I have a fairly large dipole, they cancel out. And because they cancel out, this molecule ends up being non-polar. Okay? So our answer here is going to be non-polar. All right. So I want you to do that same thing for all the rest of these molecules. I want you to figure out how many total electrons there are, draw that Lewis structure, figure out what's going on around that center atom, figure out the molecular and the electronic shape, build that molecule in that pHET simulation so that you can get the shape and the bond angles, and then use that shape in that three-dimensional and the electronegativities to determine whether these molecules are polar or not. And then once you've got this all filled out, then you can use your answers to answer the questions that are on the Canvas module for this lab. Okay? If you have any questions, please email me or talk to me in class. Have an excellent day. We'll talk to you later. Bye.